YouTube, we're going to continue our discussion in this video of solving polynomials of like higher degree that are unfactorable by utilizing what we call the rational roots test. Okay, the rational roots test, which was a nifty little way of generating a list of potential rational roots that would go into something, because let's face it, as I already mentioned, you see two polynomials I've listed here, f of x being a fourth degree polynomial and g of x being a third degree polynomial, and both of which I've made it so that they are not factorable things. Okay, so if you were being asked to solve something that's not factorable, it's kind of hard to do when you don't know any factors. So the best we can do is we can at least generate a list of potential factors that go into them, starting with f of x over here. So now f of x, you'll notice that it has all integer coefficients, and that was kind of a requirement of our rational roots test, but we can actually make a list of potential rational roots that would go into this function by listing all of the factors of the constant term, -6, over all the factors of the leading coefficient 1. So we'll start with the factors of 6 there. We say 1, 2, 3, and 6 are the factors of 6, and the factors of the leading coefficient here are plus or minus 1. So now basically writing this out in roster notation, we say the set of numbers that could potentially go into this are 1 over 1, so plus or minus 1. These are all over 1, so basically all the top numbers there. This is the potential list of zeros that might go into it that are rational. Okay, so at this point we'd have a list that we can at least guess from. If there are any rational zeros, they are listed right here. Okay, and we'd probably start by checking 1, positive 1, see if it works. Now before we do that, I do want to mention a few things about this. It is good to review our knowledge of polynomials. We say it has a positive leading coefficient and even degree, so the end behavior would imply that it starts up on the left and ends up on the right. Also that since it's fourth degree, the fundamental theorem of algebra says we have to have exactly 4 zeros when we complete this process, of which 4 of them might be real, but if not 4 of them, 2 of them could be real, or 0 of them are real. But we have to have exactly four complex zeros. And also this, if you were doing this, even if you generated this list right here, if you got a graphing calculator, we would graph this puppy, okay? So anyways, hey, just to help you out, I already graphed it. So take a look at this. You will see that we have a 0 at -1 and a 0 at 2. Now you might be saying to yourself, why is this crazy man already telling me 2 of the answers? He made me create this list of potential rational zeros just a moment ago. And the bottom line is this. I would create the graph simply because it's the sake of convenience. So you get to use a graphing calculator, why not use it? I also know at this point, looking at this, that I have 2 real zeros, so if it's a fourth degree thing, my other 2 zeros must be complex. And the bottom line is this, I know that if I were to not have a graphing calculator and check by checking 1 on that list, 1's not going to work, -1 is, okay? So for the sake of time, let's say, look, I know I have a graphing calculator. I'm not going to sit here and guess 1 first. I'm going to use the one that works. Let's just be honest with ourselves here. So setting up this array, we say our coefficients are 1x to the fourth. We had -1x cubed. We had positive 1x squared. We had -3x to the first. And then -6 is a constant. And we know that we want to check -1 first because it seems like, hey, that's going to work. So we'll go ahead and drop down our 1, and actually I'm going to be so bold, I'm going to be egotistical right here. I'm going to say 0. I'm very certain that -1 works, and maybe it doesn't. Maybe my vision is going bad, but on a graphing calculator even, you'd probably be able to tell that. I say graphing calculator because it has not as sharp a contrast, of course, as GeoGebra. But anyways, let's go ahead and get this party started. We say, okay, so -1 times 1 is -1. That plus that is -2. Times -1 is 2. This is 3. Times -1 is -3. -3 plus -3 is -6. And then flipping the sign with that -1 right there, we get 6, and there's our remainder of 0. So at this point, we happen to know that one of our zeros is -1. This is a fourth degree thing. Now, that means we have 3 more zeros left to go. At most, 2 of them could be complex, and at most the other 3 could be real. We'll see how this works out, but what I want you to notice is this. Let's go ahead and drop our coefficients back into our quotient here. We say, okay, so let's see, constant, first degree, second degree, sorry, exponent is 3, so we say x cubed minus 2x plus 3x, sorry, this is plus 2x squared, plus 3x minus 6. Now, the reason why I'm putting these back in is just to illustrate this. Once you've found a 0 that goes in, works perfectly. Lovely, man. We know -1 is one of the zeros. The thing you've got left over, of course, is of lesser degree than what you started with, and chances are it's actually factorable. And I love this example because it's got a factoring method that you probably haven't used since Algebra 1, and I refer to it as chunking. Okay, chunking. Now, what we're going to do is we're going to chunk the first two terms together and the second two terms together, but you use this method when you have a polynomial that is of third degree. Okay, and you notice that I put this plus sign right there inside the parentheses. If it was a minus, that minus also has to go with the 3. We're going to squeeze a plus sign out here. It's just the bottom line is that sign right there has to stay on its term. So if it was negative, it's got to stay on your 3. What we're going to do is we're going to find the greatest common factor between these two first terms, and we say, well, that would be x squared. So we say x squared, and that would leave behind x minus 2. We say plus, now always write this plus. That was just my plus right there. What's the greatest common factor of the second two terms? Now, what we want to be true is we want it to leave behind x minus 2 when we do factor something out. So we say plus 3, oops, let's do this in orange there. We say 3x minus 2, and you notice we did. So we're saying now, this times this plus this times this, what do they have in common? Well, they both have an x minus 2 in common. So why not kind of like reverse distribution? Let's factor that out front. So we say, okay, so well now we've got x minus 2. And then x squared plus 3 would be left over once we factor those two things out. So looking at this now and setting it equal to 0, it's easy to see that, well, we can set x minus 2 equal to 0, and we can set x squared plus 3 equal to 0. That's easy to do. And x minus 2 equals 0, well, then that implies that x equals 2 was one of our zeros. And that's really easy to go back over here and say, well, look, the 2 was our other real 0. So where are the complex roots coming from? Well, from this expression that we got right here. X squared plus 3 equals 0. Now if we subtract 3 from both sides, we get, x squared equals negative 3, taking the radical of both sides, we get x equals I times positive, a radical positive 3, and then we need to put a plus or minus in front of this. So we say plus or minus I radical 3. You'll see some textbooks, and this is appropriate too, we say plus or minus radical 3 I, and just know that that I is off on the side. It's not inside the radical. So our other zeros were plus or minus radical 3 I. So we had a total of 4 zeros according to the fundamental theorem of algebra. That's how many we're supposed to churn out in the first place. And I think it'd be a good time to mention that, hey, notice by the way, both of our complex roots, they were conjugates of one another. Complex roots always occur in conjugate pairs. So now that was kind of a quick example of how we use this rational roots theorem. Let's go over here and do it with g of x. G of x on purpose because I'm giving us a non-1 leading coefficient for the first time. So I say we go ahead and start by generating our list of potential rational zeros that could go into this. We can do this test because we have all integer coefficients. We say, okay, so P over Q, where the top is all the factors of the constant term, so 3 and 1 are the factors of our constant term 3 here. And our leading coefficient 2, well, it's prime. We say plus or minus 1, plus or minus 2. And I think it's useful to write this out in roster or set notation, okay? So we'd say plus or minus 1 over 1, which is 1. Plus or minus 1 over 2, which is, get this, a half. First time we're seeing something like that. So 1's exhausted. Let's go on to our 3 here. Say plus or minus 3 over 1, or just plus or minus 3, and then plus or minus 3 over 2. So now, we haven't taken a look at the picture of this yet. It'd be a really good thing to do right now. But I've already kind of put this equation in. We'll pop it up there and we say, all right, so our third degree thing, if I can click on it, there it is. You'll notice that it actually does. Hey, get this, it has 3 real zeros. So good news is we're not going to find any complex zeros on this one. It's degree 3 and we've got 3 x-intercepts. It is very obvious at this point that negative 3 and positive 1 are roots of this function. Now the reason why I opted to go with this example is because it leaves the possibility open for this half right there. If you're looking at this graph like I am, you'll notice that a half kind of looks like a half might be a 0, one of our rational zeros, okay? So, you know, again, if you didn't have a graphing calculator of this entire list, we'd start by checking 1 first. We'd synthetic, substitute or divide with 1, and you notice that 1 would work here, and that's exactly what I'm going to do. So we'll go ahead and set up our array and take a look at what's left over. So we say, okay, so we have coefficients 2, 3, negative 8, 3, 1. So here we go. We got 2 times 1 is 2, plus 3 is 5, times 1 is 5, plus negative 8 is negative 3, times 1 is negative 3, and negative 3 plus positive 3 is 0. So this means 2 things to me. 1, we didn't leave a remainder, and 2, when we plug x equals 1 into the function, which by the way is so totally a 0, we were at a height of 0. That is, our graph is on the x-axis. So leftover, again, let's just write the leftover out because leftover is going to be a lot easier to factor than what we were left with. Oops, wrong button, I meant my X key. So we'll say we factor this. And the reason why I like this example also is because people tend to not like to factor trinomials with an a value of 1. But we gotta stop. We gotta stop that, people, because it's not that bad. So we say, all right, so with our FOIL, we need to put, with our first here, we need to put two things that multiply out to be 2x squared, and simply put, that's just 2x and x. And then we need to do our L, or our last term on our FOIL. We need two factors that multiply out to be -3. So what if I put, like, say, +1, -3? Would this work? So I tell you one thing, we're going to get 2x squared in the front, we're going to get -3 in the back, but we need to check our outer and our inner. Those are really the only two we need to check. And you notice that if I took 2x times -3, I'd get -6x. And then 1 times x is +1x. And hey, what do you know? I actually got 5x, which is our middle term here. So if these are my factors now, sweet dude, we can just set those equal to 0. And by the way, if you set x minus 3 equal to 0, you get x is 3. And if you set 2x plus 1 equal to 0, you get, have I made a mistake here? Have I made a mistake here? Yes, I did. Yes, I did. Okay, so by the way, I hope you're paying attention. You see my mouse here. This was a +5. I am a doofus. Okay. By the way, this would not work then, our factoring method there. We would have to go back and switch our signs around. So this was a +3 and a -1. So now when you set x plus 3 equal to 0, you get -3. That's better. I was like, wait a minute. And then 2x minus 1 equal to 0, you get x is +1/2. And of course we had the 0 of 1 from earlier. So we say there are 3 real zeros, and totally support this with the evidence from our graph here. So yeah, another video that we had major success with using the rational roots test.